Welcome back to the channel. 1000K Sharing Channel is a multi-information channel. You can find a story, a lesson, entertainment or mystery discovery, or a news or event that just happened, etc. Therefore, we hope you will find a lot of useful information when watching this channel. An easy to understand and close way about high entropy. A simple approach for us to have a rough idea about this new material, and hopefully have more applications that bring practical benefits to science and our own lives in the near future, and for the present. Breaking the boundaries. Korea's high-entropy alloy and its transformative potential. In an extraordinary leap forward in materials science, researchers from the Pohang University of Science and Technology, POSTECH in South Korea, have unveiled a revolutionary invention, a nickel-based high-entropy alloy, HEA, that can maintain outstanding strength and flexibility across an exceptionally wide temperature range. This groundbreaking material, crafted under the leadership of Professor Hyoung Seop Kim, is poised to redefine how industries approach challenges related to extreme environments, from aerospace engineering to automotive manufacturing and even future space exploration. Their research, published in the prestigious journal Materials Research Letters, has already attracted widespread attention from industrial sectors and scientific communities alike. At its heart lies a simple but transformative promise: materials that do not fail no matter how harsh or volatile the environment becomes. Understanding high entropy alloys. To appreciate the significance of this invention, it's important to understand what sets high-entropy alloys apart from conventional metals. Traditional alloys, like steel, bronze, or brass, are typically composed of one principal element, mixed with smaller quantities of other elements to enhance certain properties. However, these mixtures often exhibit weaknesses when exposed to extreme conditions, especially drastic changes in temperature, leading to fatigue, fractures, and loss of strength over time. High-entropy alloys, HEAs, flip this model on its head. Instead of relying on a dominant element, HEAs are composed of 5 or more elements in roughly equal proportions. This results in a random atomic structure, where atoms are distributed in a chaotic yet stable manner. This phenomenon, called high configurational entropy, gives HEAs unique and desirable properties: superior strength, flexibility, corrosion resistance, and remarkable durability even under severe stress. By moving beyond the traditional metallurgy, playbook HEAs offer a glimpse into the next generation of materials, ones designed not by adjusting old recipes, but by reimagining atomic structure itself. The Hyperadaptor, a new era for materials. Professor Kim and his team introduced an even more novel concept alongside their alloy: the Hyperadaptor. The Hyperadaptor approach envisions materials that are not merely resistant to change, but are adaptive, capable of maintaining mechanical performance despite sudden shifts in external conditions, such as freezing cold, searing heat, or rapid pressure changes. The high-entropy alloy they developed embodies this concept by integrating specific nanoscale features that enhance its resilience. At the core of this innovation are L12 nanoparticle precipitates, tiny ordered structures embedded within the alloy's matrix. These nanoparticles act as reinforcement agents, preventing the metal from deforming or weakening even when exposed to stresses that would typically compromise conventional metals. Moreover, the alloy's stress-adaptive microstructure allows it to absorb and redistribute external forces efficiently, preserving its strength and flexibility. This makes it uniquely suited to applications where reliability under fluctuating or extreme temperatures is non-negotiable. Unmatched capabilities. Strength across extremes. The most astounding feature of POSTECH's HEA is its ability to perform consistently across a temperature range from 196 degrees Celsius to 600 degrees AC. This is a remarkable achievement because most metals either become brittle at low temperatures or lose their strength at high temperatures. Such temperature stability unlocks opportunities in industries that have long struggled with material failures. In critical fields like aerospace, where parts must withstand frigid outer space conditions and burning atmospheric re-entry, or automotive manufacturing, where engine components endure extreme temperature cycles. Traditional materials often fail or demand complex protective measures. The Korean team's alloy offers an elegant and durable solution. Components made from this HEA would require less maintenance, last longer, and ensure higher safety standards, directly translating to lower operational costs and increased performance reliability. Real-world applications, transforming industries. The real excitement around this invention comes from its potential applications. Here's how POSTECH's high-entropy alloy could reshape various industries. Aerospace engineering. Space exploration demands materials that can survive the most punishing environments imaginable. Near absolute zero temperatures in the vacuum of space, rapid heating during re-entry, and continuous mechanical stress. Lightweight and reliable metals are critical for spacecraft hulls, engines, and support structures. POSTECH's HEA could become the backbone material for spacecraft, satellites, space stations, and even future lunar or Martian colonies. Its combination of strength, flexibility, and temperature resistance can dramatically enhance mission safety and longevity. Furthermore, because space missions often hinge on the reliability of every single component, the development of temperature-insensitive metals like this HEA could lower the risks of catastrophic failure. Automotive industry internal combustion engines and exhaust systems experience intense heat cycles during operation. Existing metals often degrade over time, leading to inefficiencies, costly repairs, or dangerous failures. By incorporating POSTECH's HEA into critical engine parts, manufacturers could produce vehicles that are safer, more efficient, and longer-lasting. Moreover, in the era of electric vehicles, thermal management remains a major concern. Advanced alloys could provide essential solutions for battery housing and motor components, where thermal stress is a constant issue. Heavy-duty vehicles, like trucks, buses, and construction equipment, would particularly benefit from materials that can endure continuous mechanical and thermal stress without degradation. Energy and infrastructure. Energy production facilities, whether nuclear reactors, geothermal plants, or offshore oil rigs, face extreme conditions that can corrode and weaken traditional materials. Pipes, turbines, and structural components made from high-entropy alloys would be far more resilient, reducing maintenance costs and downtime. In particular, the HEA could play a transformative role in next-generation nuclear power plants, which require materials that can resist radiation damage, high temperatures, and mechanical stress simultaneously. Similarly, pipelines carrying hot or cold substances over long distances could become far more reliable if constructed from materials that don't suffer from thermal expansion or brittle fractures. 4. Defense and military applications. Military vehicles, ships, and aircraft must perform reliably under battle conditions, where rapid temperature changes, mechanical impacts, and exposure to the elements are common. Armor plating made from high-entropy alloys could offer enhanced protection without the traditional weaknesses of steel or aluminum. Furthermore, missile and rocket components could benefit from the alloy's ability to endure thermal shock and mechanical loads, improving operational performance and mission success rates. Medical devices. While less immediately obvious, the healthcare sector could also benefit. Surgical instruments, implants, and prosthetics often require materials that are biocompatible, corrosion-resistant, and mechanically stable. A high-entropy alloy with these traits could enable longer-lasting implants and more durable surgical tools. In particular, the ability to maintain mechanical integrity in varying temperature and stress conditions would be critical for life support. Devices or implants intended for extreme environments or long-term deployment inside the body. Building the future. Beyond the laboratory, while the immediate excitement is about its properties, POSTECH's innovation also signals a broader shift in how humanity will engineer materials for the 21st century and beyond. Professor Kim emphasized that their high-entropy alloy represents more than just a new product. It's a new class of material. By breaking free from the traditional limitations of alloy design, The hyperadaptor concept opens the door to a future where materials can be tailored precisely for their intended environments, offering reliability, efficiency, and safety at levels previously unattainable. Furthermore, as industries move toward more sustainable practices, durable materials like this HEA could reduce waste, lower the carbon footprint associated with frequent part replacement, and enable longer-lasting products across multiple sectors. This discovery is particularly timely given the global challenges we face today. Climate change, space exploration, clean energy production, and advanced transportation systems all demand materials that can do more, last longer, and perform better under unprecedented conditions. Final thoughts. The invention of a nickel-based high-entropy alloy, capable of thriving under extreme temperature variations, is more than a scientific milestone. It is a transformative step toward a more resilient, efficient, and daring future. POSTECH's breakthrough has shown that by thinking differently about how we build materials, embracing randomness, complexity, and adaptability, we can unlock capabilities that once seemed impossible. As industries begin to integrate these next-generation alloys into real-world applications, we may soon find ourselves living in a world where machines are stronger, vehicles are safer, exploration is farther reaching, and technologies are more enduring, all thanks to the bold vision of a team of Korean scientists and their Hyperadaptor dream. Thank you for watching until the end of the video. If you find the information useful, please like, share, or leave a comment so we know what we need to improve in the next videos. Thank you very much.